Okay, so today's video is going to be about quantum mechanics. So in quantum mechanics, today I will be talking about whatever I have, whatever information I have on quantum mechanics. We will talk about the experiments, about the phenomena, then we'll talk about the connection, okay. So when we focus on these in extra, we will add something extra as well. Okay, so first of all we will talk about the phenomena. Before that, let's talk about quantum mechanics. How quantum mechanics is different, how it is different. By quantum mechanics, when we study quantum mechanics, what happens is that in classical physics, when we talk about a car or a truck moving, if we know its initial position, suppose we know its SWOT, we know its distance, we know its initial velocity, final velocity, acceleration time, we can calculate, and some other things we can calculate in future what will be its speed, how much distance it will travel, and how far it will travel, what time it will take for it to travel. We can predict all that. That's what classical physics allow us to do. Classical physics allows prediction to take place. And the best example of it is projectiles, the study of 2D motion. Projectiles, 2D motion. This is projectiles. This all comes under, this all comes under classical physics. Okay. This is, so we have F equal MA, then we have A equal VT, W equal mg, 1 by 2 mv square. We have these in classical physics. But when we talk about, then there's one more, which is, okay, this is about everyday physics. This is everyday physics. Okay, then there's other physics which is at macro level. Okay, and for that it is the study of planets, about space-time, about space, about curvature of space. That is also regarding physics of at larger level. And Einstein is famous for that. Special theory of relativity is famous for that. relativity, relativity. Okay, but we'll not talk about it that much, but just know that in classical physics predictions happen. But now that when we come to quantum mechanics, okay, now the best example for quantum mechanics, let's suppose I have a particle. Now this particle is in different nature when observed sorry, not absorbed, observed, okay. It has different nature when observed and different nature when not observed and not. Okay, what I mean by different nature is, okay, first thing, not first, we'll do like a little physics. When I talk about this particle, first of all, I will talk about when it is being watched. Someone is watching it. Okay, what will happen? This particle will have a definite position. It will be a point particle. It will act as a particle. Okay, it will act as a particle. It will follow one direction. If let's suppose this is the direction, it will either go here or here. Plus, after that, it will, one property is that it can exist in more than one states, but when you observe it, it will only be a particle. And there's one experiment, and in that experiment it's everywhere, but when observed it's at definite areas like these. Definite areas mean they're visible. You can actually, because when they take this one path, either they will go here or here. Okay, so also when we talk about one thing here we have to notice is, when we talk about its, this is what is x. First of all, let me know x is position. Okay, so when we talk about x, if you are measuring its x means position, at that time, if this is high, there's one more quantity which you can measure, but that quantity's preciseness will decrease. That is momentum. So x, wait, let me write, knowing x decreases value of preciseness of momentum. Position. So the formula is Okay. Then this is what we call this. This is Heisenberg uncertainty principle. Heisenberg uncertainty principle. Okay. Then we can know where it is using can know where it is in our area. How? We can use psi of x and t, depending on if you need t or not. Either this or this. Prediction. But result is different. Okay. So then all this, we will keep one thing common here. H bar and H to denote smaller level or nano level. Okay. Then there, this is when this all happens when you observe it. Okay. But depending on what type of observation you do, if you look at this, there's some conditions over here. If you're observing it, its velocity, or its what do you call that, position is known, which decreases the precision or knowing of momentum. So we can say these equal 1 over constant. Okay, it's a constant, equal constant. What else can I say? Remember, this is observed. Okay. Now, it's same for little bit about observe without not observing, but how I will say it is different for observation. Now, not observed. Not observed. Observed. Sorry. Not observed. Okay, not observed means not observed is a whole cross. Okay, so there's no observation. Now this particle is not a particle anymore. Not a particle anymore. What is it? It's actually a wave now. Now it's actually a wave now. Okay, now it's a wave. Okay, there's an experiment I would like to talk about first before we go on. This is known as Young's experiment, Young double-slit experiment. So this is what I will be talking about. Okay. So when this light wave, when it's right now it's parallel, okay, at this point what happens that it curves. This is called diffraction. Okay. Now then again two slits again appeared. So again now again now the wave is split into two. Okay, now here the key point is here. At this point where the two waves are interacting, this is known as what do you call this? Interference pattern. This is interference pattern. Okay. Plus, at this point, high chances particle being there. Okay. When this is something as back screen is what gives us the result. So if I write the result, if I make the result of this line as wave, this is what I would get. And our result will be the amplitude of this wave. It will be double the amplitude. Okay, this amplitude. Okay, then one more thing, if we have two waves coming towards each other, okay, and if they have same, when they add up, what happens is we get a double. So this is, what is this? A. What is this? A again. So the combination will be two A, because we combined their amplitude over here and here. This is called constructive waves. Amplitude combines. Okay. So A plus A equals to 2A. Okay. Then okay, so then what is it again? Yeah. Okay, so then let's talk about the superposition. Superposition. This is what superposition sign looks like. Okay. Now, what if I open this wave function? Open the wave function. What we get? This is what we get. Or first of all, we just start with basics. Okay. So here, what I mean is that if there's a particle and it's spinning, we know that when we talk about the particle spin, it's actually spinning up as well as down, both. Okay, superposition. Over here, if I write this particles without when it's observed, this is what it will look like. Either it will have up, spin, or it will have down, spin. Okay. Then, when we talk about the quantum superposition state, it's spinning both ways, up and down. So when I combine it, yes, I'll talk about this. This is how it will be. This as a superposition, this is how I'll say it. Okay. Sorry. Different colors. See how we can say it. It is, but it's different direction. Different direction. Different. Okay. Yeah.